I haven't given a talk in person in 2 years, so please forgive me. I'm not sure how it works. But I would like to talk about this paper that appeared in July with my student in Oxford, Aurea Magoreanu, about the Coulomb range of 5D theories. How do I? So let's motivate and put in context, but really it's very similar in the very broad context to what Thomas Grimm was discussing just now. So, but my focus will be on quantum field theory, not gravity. And so we know that quantum field theory by itself is very hard for various reasons, including at strong coupling. It's hard to talk to mathematicians about string theory because they have no idea what we're talking about. And when we introduce supersymmetry, at least, it gives often a more geometric approach to quantum fields that allows to bridge also this divide between math and physics, which to me personally is a motivation. In string theory, we can often engineer supersymmetric quantum field theories using both open and closed strings. And in this talk, I will focus on what is often called geometric engineering of supersymmetric field theories, which is when we use the closed string sector really to engineer gauge fields and quantum field theories in general. So recall the basic framework that we had in the previous talk. We have just a compactification to 2D dimensions of 11D M theory or 10-dimensional string theory. And then essentially we will have an effective field theory at low energy, including gravity, where the Newton constant is essentially the inverse of the volume of the compactification manifold. Thank you. So in the present context, we want to decouple gravity, so we do that by taking a very large volume, or really more specifically from the start, we will consider non-compact spaces.
It's dangerous to use one stick when it gets the screen. I will first.
I won't touch the screen. All right. So yeah, so we decompactify already. More specifically, we from the start consider a non-compact Calabi threefold, which is much more a general class of things than things you can actually decompactify from a compact setup. Specifically, I will be interested in things which, in some sense, will have no scale from the start, so that we engineer conformal field theories. Those will be canonical threefold singularities. They're essentially cones where, in some sense, you see a Calabi condition in the algebraic sense. And we will place ourselves in 11 dimension in M theory. And then there is this Q identity, which is 11 equal 5 plus 6. And since the Calabi is 6-dimensional, my quantum field theory then will be 5-dimensional. And so, of course, this is a setup that was considered long ago. The existence of superconformal field theories in 5 dimension were first shown by Seiberg in '96, and then engineered through this kind of method by Morrison, Seiberg, and many others in the '90s. But in the last few years, there's been a regain of interest in this kind of setup for various reasons, and that's where we are standing. So this is the outline. So I will introduce a rather large introduction about really Seiberg-Witten geometry. So 2D conformal field theories with 4D, sorry, n equal to supersymmetric theory, in particular SQCD. And then I will discuss this setup in the slightly more formal sense of a geometric setup of rational elliptic surfaces, and using that revisit a bit the well-known story about rank 1 theories. But we'll see that, I mean, why I want to go through 4D is because 5D then naturally fits in there, as we'll see. There will be some small comments about modularity here and there. And then hopefully the last third of the talk, I will actually discuss the main new result in some sense about 5D and CFTs and their circular compactification to 4D.
Just too loud?
Sorry?
No, it's not very loud.
Okay. I mean, yeah, I guess I'm running COVID, but I'm pretty sure I don't have COVID. I haven't seen a person in 2 weeks, so I think I should be fine. So let's start with the introduction. So yeah, let's go back to basics. So there was these 2 papers, right, about other famous by Seiberg-Witten in '94. So what did they do? They were interested in 4D equal to supersymmetric gauge theories with the SU2 gauge rule. So those are so-called rank 1 theories. And we consider n equal to supersymmetric vector multiplets, which include the scalar phi. And the scalar potential includes this term, which is phi, the commutator of phi bar phi, so phi and the adjoint of SU2 squared, so that in the vacuum in particular, you can diagonalize phi. We'll consider the SQCD setup. So SU2 gauge theory was also matter in hypermultiplets in the fundamental representation of SU2 with masses mi for, let's say, the NF vector multiplets. Recall that because of asymptotic freedom, I mean, if we require asymptotic freedom, we can at least at most have 4 hypermultiplets because the beta function is 4 minus NF, the one-node coefficient. This SPCD has a simple flavor symmetry algebra, just rotating the hypers among themselves. So if you have no masses, then the hypers are really 2NF half hyper, because the 2 and 2 bar are equivalent for SU2. So you have SO2NF flavor symmetry. If you instead give a common mass to all the hypermultiplets, you break it to a UNF flavor symmetry, and in the generic case with generic masses, you have only U1 to the NF symmetry. On a generic vacuum, on the Coulomb range, then as we said, we can diagonalize phi, and then we'll have X mechanism, and we'll be interested in what happens to the low energy photon on the so-called Coulomb range. So when you give this kind of prescribed depth, and then at low energy along a given vacuum, A, and its fluctuation, now we'll still call A, is the low energy photon, or more precisely the scalar associated to the low energy photon. And the problem that Seiberg-Witten solve is to give the exact solution for the full low energy effective action at 2 derivatives. So you would have terms like this when you have the usual Maxwell terms, kinetic term for scalar and so on. Most of this structure is determined by supersymmetry, but there is an overall holomorphic function that determines the effective gauge coupling for any value of the vectors. And to determine this tau of A is a challenge. It's determined really, tau itself is determined as second derivative, holomorphic derivative of a holomorphic function for the free potential. The Coulomb range is parameterized then by a gauge invariant operator, really. So A is just in the semi-classical approximation. That would be what I really should consider. I mean, the gauge theory is gauge invariant quantities, so that would be trace of phi squared, which is A squared semi-classically from these things, but of course there will be quantum correction to the quantum depth. So U is this quantum depth of phi squared, and then the A very large or U very large is the weak coupling point. So that's where semi-classical approximation is valid. But the challenge is to integrate in, so to speak, at small u, see what's going on. So recall that at low energy, at a given fixed u, there is no, I mean, there is electromagnetic duality. So you can always call a photon or electromagnetic dual. And well, the Maxwell equation are SL2 invariant. And so you can, well, it's a choice. So we will pick a choice that is determined by the UV, by the X mechanism from S0 to U1. But then interesting could happen at strong coupling. So electromagnetic duality in general would then relate essentially electrons to monopoles, right? Like in the usual Maxwell equation. And so in the dual photon, there will also be a scalar called A dual, and those scalars can be rotated by a general SL2Z matrix, where S and T are the usual generators of SL2Z. You can show that with supersymmetry, the electromagnetic duality is determined also by the free potential, in the sense that the dual photon is just the derivative of the free potential with respect to A itself. And then just by this, which you can take as a definition of A dual, then my period is dA dual over dA. And then, well, that's the picture of the U plane. So we have a one-dimensional plane, U. At large volume, at large distance, large U, there is a weak coupling point. We are at some base point there in the strong coupling region, say, and there might be other things that happen when you go around. So what happens, what we're interested in, we have a fixed point. We can go around and come back. In general, there might be a monodromy in the definition, in the periods that we measure at this point. When there are singularities, there can be monodromies, and the fact is, there could be, or in general, there must be strong coupling singularities, and that's the one that Seiberg-Witten determined for pure SU2 and so on. Yeah, so I will think about this U plane as a projective plane in much of the following, but really, I mean, It's still a non-compact space. It's just convenient to put it as, to think of it as pi1 with like the North Pole fixed, which is the point at infinity.
So the singularities corresponding to strong coupling are at finite distance.
There are finite distance there, and that would be like large U in the, which is a typical log things determined by the beta function in the metric. So the insight of Seiberg-Witten is that, well, what do we know physically about tau is that its imaginary part is positive, right? Because it's this part, the kinetic term, and it's transformed naturally under SL2Z. From this, tau will actually transform in a modular way by linear, partial linear transformation or whatever they call it. So, well, the one geometric object that transforms this way is precisely the modular parameter of a torus or an elliptic curve. And so we can postulate, they postulated that this is what happened. So you introduce the auxiliary construct. So this is still my U-plane in blue, but over each point on the U-plane, there is an elliptic curve. And in general, it's just a smooth elliptic curve with a choice of origin. But at the singular point, it will pinch in some prescribed way. And that's the geometric realization of these physical singularities. So this setup is what is called the Seiberg-Witten geometry, or sometimes the Seiberg-Witten curve. I mean, so it's interesting when you talk to mathematicians, you realize we have very low language in physics. So by Seiberg-Witten curve, we really mean a one-parameter family of elliptic curve, right? That's what the Seiberg-Witten geometry is in this case. No, yeah, as I said, it necessarily has singular fibers. There is certainly the large U singularity at U equal infinity, but then there must be at least one in the interior too, so that because the monodromy group, if you go around there, the monodromy, then there must be the same monodromy if you go around all the other singularities. That's, I guess, the constraint I put there too. Right, just because you can compose, you go onto a path, there is a particular monodromy, you compose the other one, so you just compose the matrices here, that acts. And so if you go around all the paths, you get the identity. Okay. So the singularity at infinity can be determined just by recoupling semi-classical consideration. It's just determined by the beta function, which we said is 4 minus NF. That's the beta function of SQCD. Yeah, so the actual singularity will be minus t to the 4 minus NF. That's what is called in the parlance I star singularity, I star 4 minus NF. You can have what I would call simple singularities, or ordinary Seiberg-Witten singularities in the interior, which are so-called IN singularities, when you get t to the n for an IN without the minus. That's what is called the multiplicative fiber. At any given point, this is the conjugacy class. So at any given point, if you fix a basis, electromagnetic basis, then the particular model will be conjugate to this or this. So we fix that to be the one at infinity, but then the actual singularity at the interior, the I1 singularity of Seiberg-Witten's theory, will be conjugate to T. So in general, the physics of this I1 singularity is that a single diagon of charge MQ becomes massless. So T would mean like just an electron become massless, but if a monopole or diagon which monopole charge M and electric charge Q becomes massless, you just conjugate like this. You get this. So those are like the simple Seiberg-Witten singularities, and it was also noticed after Seiberg-Witten papers that all just mathematically all the allowed singularities in such an elliptic fibration are classified by Coulomb from the 60s or 70s. And there is a finite small list of possible singular fibers, and those are their names. So there is IN, I star, you probably all have seen some version of that. And this is the particular conjugacy class of the monodromies for the so-called type 2, 3, 4 and type 2 star, 3 star, 4 stars. Okay, so if for massless SQCD, this is the solution of Seiberg-Witten. Just schematically, you see what are the singularities, and then you can actually write curves, one parameter family of curves that have these singularities. Here I'm talking the case of the massless SQCD. So this is the celebrated one that you've all seen, right? For pure SQ2, there are two singularities. There is a diagon that can become massless, a monopole, let's say, and a diagon that become massless. There is the two symmetry that exchange the two. For n equal 1, there are 3 particles, diamonds that become massless. There is a Z3 symmetry in that case. There are 2 I2 singularities, so there is like 2, in some electromagnetic dual frame, it's just like a U1. The low energy theory at the I2 singularity is just like 2 electrons coupled to the effective U1. That's n equal 4, it's an I4 and I1 singularity. N equal 3, sorry, n equal 4 is a conformal field theory in the massless case, because the beta function vanishes. And you see that there is a single singularity at the origin that's related to conformal invariance.
In the massive case, the singularities will split.
Oh yeah, in the massive case, in those cases, if you have generic masses, all the singularities split into I1s. So in general, there are ns plus 2 singularities. So in particular, the I4 star, it actually can split into 6 I1 singularities for generic masses. So one thing that we kind of revisited and I think clarified in the paper with Oya is the global symmetry of some of like non-Lagrangian theories, but even in like the SQCD example, it kind of gives a nice picture of how to read off the global symmetry from the infrared, and that's what I would like to explain a bit. So we said that the global, so I told you at the beginning what was the global symmetry, but I didn't specify, I just told you the algebra. But in general, you want to specify a global symmetry group, which will be, by definition, the group that acts effectively on gauge-invariant states. So for instance, I tell you that it's an SU2 symmetry, you want to know if it's SU3 or SO3 or SU2, or in general, whatever global form, right? So in this case, the global symmetry of massless SQCD is easily determined in the UV, because we have a Lagrangian, and it's SO2NF, the global SO2NF, not Z2. The Z2 is just because changing signs to all the R factors here is a gauge symmetry. We can write this group for NF equal 1, 2, 3, 4, maybe in this way, which will be useful in the next slides. So let's say, NF equal 2 is SO4, that's SU2 times SU2. SO4, the double cover of SO4 is spin 4, that's the simply connected one, which is SU2 times SU2. And then the actual SO4 mod Z2 is SU2 mod Z2 times SU2 mod Z2, actually. Similarly, for NF equal 3, it's SO6, which is SU4 mod Z2. The syndicated group is SU4, so spin 6. And then you mod by Z4, that's the same as SO6 mod Z2. And similarly for NF equal 4, that's spin 8 mod Z2 times Z2. For NF equal 0, there are no flavor symmetry, but there is an interesting symmetry, which is the so-called one-form symmetry. Those one-form symmetry were introduced or clarified, defined, let's say, by a guy that comes in Seiberg-Witten almost a decade ago now. And it's just the symmetry that acts on the Wilson loop in the fundamental. So when there are no quarks here for pure SU2, there is nothing to screen the Wilson loops. They are nice observables, but there is a Z2 symmetry that just changes the sign of the Wilson loops. So we would like to reproduce this as an exercise, this global form of the flavor group directly in the IR. I will give you the answer in a bit. But let me give a partial answer, or to, in principle, to read off the flavor symmetry from the infrared in this kind of Seiberg-Witten geometry, rank 1 Seiberg-Witten geometry. Well, the first part is pretty simple, and for anyone doing F theory, that would be pretty well known. For each singularity of scalar type, you associate a flavor algebra in this way. So the IN in particular is associated to a SUN flavor symmetry. The I star M is associated to SO8 plus 2M flavor symmetry, and then there are those exotics. So 2, 3, 2 has no flavor symmetry, 3 and 4 is SU2 and SU3 respectively, and most excitingly, 2 star is E8, 3 star is E7, 4 star is E6. That's just a claim that we'll justify by the end of the talk, hopefully through string theory. Any question about this setup? So, time nearby because I don't have the time showing me.
You have 40 minutes. It's just 12. Yeah, there's no help here.
Okay. Put my-
I think it's there.
Oh, thanks. Cute. All right. So sorry. Yes. So let me now go into a little bit of technicalities. How we actually describe the curve, right? I draw some picture. If you want to do actual computation, it's a good idea to. You can write those Seiberg-Witten curves in any coordinates you like, but one nice set of coordinates will be the so-called Weierstrass normal form. You can always bring such a curve over the complex numbers in this form. It just depends on two functions of the parameter G2 and G3. That depends on U and maybe the masses. And then in this form, you look at the discriminant of this curve, of this one parameter family of curve. That is just this formula, and so you get the polynomial in U, and the root of these polynomials are where the singularities are located. So in general, for generic parameters, you will have NF plus 2 simple roots. Those are the I1 singularities. But in general, you might have colliding zeros and more interesting physics. So for pure residual, for instance, that's the formula, and that's U squared at U squared equal plus and minus 2 lambda squared, let's say, where lambda is QCD lambda, you will get Seiberg-Witten singularities. For any of the singularities, you can determine just looking at the Weierstrass form, what are the singularities. This is the table, but the point is you look at the vanishing, how it vanishes at a given singularity, the discriminant, order of vanishing, but also G2 and G3, that determines the different types. So we're interested in principle in the physical periods, which are of fields A dual and A, which geometrically will be periods of the so-called Seiberg-Witten differential over the A and B period of the Seiberg-Witten geometry curve. The Seiberg-Witten differential is such that up to a normalization, its derivative with respect to U is the unique holomorphic one form of the generic elliptic curve. And so at the first pass, we can focus on the so-called geometric period, which are just the period of the holomorphic one form. And they satisfy a standard Picasso equation that you can determine for any Seiberg-Witten geometry. So in principle, that would be the hard way to solve the problem of finding everything, right? You set up the Picasso equation, you try to solve for the period, look at the monodromy by end. One can try, it gets tedious. We did that for in a few cases of interest in 5D. Now, the low energy Coulomb range is determined then by the total space of this affine bundle, as we say, so the vibration of A, B, and A. It's affine because the A dual and A transform into each other, but they can also shift by constant because of the masses. We will consider the main player in the following will be instead the total space of the elliptic curve itself over the base B, which is the Coulomb range, the UK. And these things is a rational elliptic surface, or well, yes, essentially it's a rational elliptic surface with a section mathematically. So that just means that I have an elliptic fiber over every point there is a zero section. So there is a consistent choice of origin of my elliptic fiber everywhere, except at the finite number of points, well, including at the finite number of points really, but where the T2 degenerates, and then you need to do something to see what it looks like.
What do you need a section for Seiberg-Witten geometry?
I don't think you might. I mean, all these cases that we consider have a section naturally, and they do in the simplest type 2B geometry. It's actually an interesting question whether you could have genus 1 vibration, which are Seiberg-Witten geometry. The literature is not exactly super clear on this. It's something I would like to understand better. We can discuss at the end. But yeah, in this talk, at least I will just set for simplicity and to use useful mathematics, I will assume that I'm looking at just elliptic vibrations. So that by definition, that means I have a section, the zero section. Okay, so I will have that. In general, there is singularities, associated to this code are singularities. Whenever you have type which is not I1 or type 2, whenever there is a scalar symmetry, essentially here, there will then be an actual singularity in this rational elliptic surface F, that space. But then you can resolve it in a standard way, essentially canonical singularity. This this resolved space, which I will call S tilde, is always so-called DP9. Biomorphic to a DP9. So that means DP9 is a blow-up of pi2, at 9 points. That's what's sometimes called the half K3 surface by string theorists. So it's not a category, it's just what it is. But the nice thing about this kind of surfaces, rational surfaces, is that their second homology lattice, when you put the second homology with intersection pairing, take the following form. It's generated by the zero section, the elliptic curve, the generic elliptic curve, and then it's 10-dimensional. The remaining 8 dimensions form the shape of an E8 lattice. Okay, so in this resolve rational surface, well, you need to resolve all the singularities, and they're done in a standard. They have standard AD singularities that many of you have seen in F theory and so on. So they have a resolution where you have irreducible fiber now. When you resolve the singularity, then you get a bunch of pi ones that intersects in the shape of a Deakin diagram for an EN type or AD type singularity. So a cool thing about rational elliptic surface, and why I want for this talk to assume at least that I have an actual elliptic fibration, is that elliptic curves are pretty cool because they're also abelian groups, right? So you fix the zero, and then you just seed mod a lattice, and then you can add points on the elliptic curve. So now we have the elliptic curve fibered over the base, over the U-plane, but there is still there will still be then well, you choose a point everywhere. That's a section. So you can then add those sections. So there will be a non-trivial group of sections of this elliptic fibration. This is called the model group of the fibration. So a section just means a solution x of u, y of u of my Weierstrass equation, which is rational in the parameter u. In fact, in all these examples, you can take it to be a polynomial in u. So these points in general could have be of two types. There will be points where you can add them forever, and that's it generates the free part of the model group. So that will be the rank of the model group. There will be a rank of phi generator, and then there might be torsion sections as well, which are like of this form Z2, Zk. That just means that you, for instance, a Z2 section, you add it to itself, and it gives the zero section. So in this model group, the zero section is the origin of the zero of the abelian group.
So why are you interested in the model group? Can you explain?
Yes, I will. So rational elliptic surfaces are fully classified. They are characterized by the set of singular fibers and by the model group. The classification was done by Pearson and then checked by their collaborator Miranda in 1990. So there's two different derivations of the same fact, really. So there is a nice list, a very explicit list of 289 rational elliptic surfaces. Most of them have a distinct set of allowed singular fibers. A few of them have the same allowed singular fiber, but then are distinguished by different model values.
So in physical terms, that means that there are 289 and equal to 2 common field theories of rank 1?
Not exactly, but I'll get to that. This will be exactly the number of Coulomb configuration of the E-string theory on the torus. That will be the interpretation, but I'll explain that in a minute.
Sorry, Cyril, can I ask a question?
Yes.
The vibrations you are discussing are over the plane, or it can be any higher dimensional manifold?
What I'm doing here is over the plane. I'm just looking
just
at
over the plane. Okay, thank you.
One-dimensional Coulomb branches, yes. And there are also the mass parameters, but I treat the mass parameters as I'm not part of the base in the sense I fix them once and for all, and then I look at the U-plane, which is the dynamical parameter.
Okay.
So a basic and powerful constraint to start classifying those rational surfaces is that the sum of the order of the singularities, of the zeros of the determinant of the singularities, right? I gave you the list somewhere there. So it's a bunch of numbers here, and their sum must be 12. So that's restrict what you can combine, right? As a first pass, you just want to combine singularities in a way that it sums to 12. In fact, there are only 20 allowed configuration you can show, with this constraint and a few others, which are those. Those are the only 20 singularities that can appear in principle on the Coulomb branch of any of those theories. So that was a mathematical interlude, so let me go back to SQCD and in general supersymmetric QFTs. So because why I like this perspective and this particular nice table in Person's paper is that it gives us a bird's eye view of the rank 1 theories. So this idea in a paper we generalize in fact an idea that appeared in a paper by Garcia and Chicotti that thankfully we realized existed just before we copied it, where they had a similar picture, but they focused on essentially what I draw in color here. So what is this? These are all the possible. What is the setup here? In general, we not only want to look at a rational elliptic surface, but a rational elliptic surface with a prescribed fiber at infinity, what I would call U equal infinity. So in terms of mathematically, I don't care where they are on by one, but here I fix what is a singularity at infinity. And the claim is that that's defined what will be the UV superconformal supersymmetric QFT. So I will fix the fiber at infinity to be F infinity, and then the pair rational elliptic surface S with a prescribed fiber at infinity is define my QFT for me, my UV QFT. So the idea is that I fix the fiber at infinity, and then the fiber in the interior can vary as I vary the masses of the theory, but it's a fixed UV theory. So in this sense, here is a table then of the number of, I told you that in general, if I have, in a generic case, that would mean the fiber at infinity is not special, and it's just what we call I0, just a trivial fiber. Then that's the full classification of person. There are 289 theories. But if I fix the fiber at infinity, for instance, for Seiberg-Witten theory, we saw that in Seiberg-Witten you need to have I4 star at infinity, just from general consideration. In that case, there is a unique rational elliptic surface. You can only have two I1s in the interior, and that's it. So that's the Seiberg-Witten solution. In that sense, it's unique. If you take, let's say, I1 star, that will be SQCD with NF equal 3, SQ2 with NF equal 3, then there are 13 configurations, in the sense that what means physically is that I can start varying the masses, and then the singularity will merge and collide in various ways. And I count a configuration if it's like topologically distinct. So I can have I1, 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 or I1, I2, I1, and so on. So these are the SQCD things in red. Then there are a few others. If you have more complicated singularity at infinity, those are the ones that were noticed or discussed by Garcia and Chicotti. So let's go down there. If you have the 2 star, 3 star, and 4 star at infinity, you get the so-called classic Argyll-Glass theories. That are often called H0, H1, and H2. Those are the Argyll-Glass theories that arise in one way to construct those, so that are superconformal field theories, right? But they can be embedded in a different UV complete theory, which is SQCD itself. So if on the Coulomb branch of NF equal 1 exists these Argyll-Glass theories. In a sense, you can go from one to the other, precise sense, by putting one I1 singularities, merging it to the I3 star, getting the 2 star at infinity. And that's a particular RG flow from SQCD to Argyll-Glass theory and its Coulomb branch. Yes. So
these singularities like 2 star, 3 star, 4 star, they also sit at infinite distance.
Yes, they are all at U equal infinity. And
well, U equals infinity is
the infinite distance in the metric, it will be an infinite distance, yes.
Is that also true for the other ones in green, for example?
Think so, but yeah, I think so. I haven't tried to bound like the metric and see if it's actually finite.
In other words, in Coulomb specification are all the ones at finite distance, are they of IN type, or are they also?
No, at finite distance you can have everything happening. All of those possible scalar singularity can happen at finite distance as well.
Okay, so just knowing the singularity doesn't tell you a priori if it's at finite distance or not.
No, that's an extra thing. And for us, I want, for here algebraically, I just mean U infinity in principle if to compute the metrics if it's, but yeah. For us, we just fix the point at infinity, that's define the UV, and then everything can vary in the interior. But I would assume that in the proper physical metric, there will actually be an infinite distance.
Sorry, Cyril.
Yes.
I thought that the Argyres-Douglas theories appear in theories which are SU3 and higher, with higher rank. How do they appear in this diagram?
No, they also appear, so the type H0 appears for also SU2 with n equal 1, H1 appears for SU2 n equal 2, and so you can always tune the mass. In this case, you essentially tune the one mass to lambda, and at this point, there is this Argyres-Douglas theory that appears. This is a paper by Argyres, Plesser, and Seiberg.
I see. And in that case, I remember that the mutually non-local massless states appear. How does this shows in the singularities?
I will show a picture of that maybe. Actually, yes.
Thank you.
So, yeah,
Can I also ask a question? So from the elliptic surface perspective, there's the fiber infinity is not distinguished, right? This is when we put the special geometry on the base that's the
yeah, it's not distinguished for us. I mean, for this, geometrically, just an extra thing. Mathematically, just a fibration of pi1, but physically, pi1 is really a convenient way of seeing C, the physicals, and we want to have infinite VF, and so that's my point at infinity.
So from this picture, can you see the list of SCFTs? Which subset?
Yeah, so those are 3 SCFTs, right? We'll get to that. There are 3 more here. Those are like the type 2, 4, 2, 3, 4, sorry, at infinity. And this, I will show later, hopefully, that this corresponds to the so-called Minan-Nemensky theories. So that's essentially how they were discovered, but in a slightly roundabout way. So here, what I'm doing, following essentially Closset, is that I'm defining the UV theory, some kind of UV theory, by fixing the fiber at infinity, and then anything can happen in the interior. But that means, like, in general, you get a mass deformed Minan-Nemensky theory, for instance. If you collide all the, in general, I1 singularities to the origin, then you get pictures similar to this one for the conformal, the Lagrangian theory. This one, right? In general, you get a fiber at infinity, and then you get the fiber with the conjugate monodromy, the inverse monodromy there. So in this case, actually, for Minan-Nemensky theory, if I fix, let's say for the E6 theory, the E6 theory, when then we type 4 at infinity, that means that in the massless theory, I will have type 4 star at the origin. And that's what realized the E8 ferrosymmetry, in particular, E6 ferrosymmetry, sorry. And that's how they were like conjectured originally by string theorists. Like, oh, well, then it was constructed later in various ways, but actually I will explain one way to construct it also from this picture. But just mathematically, you see that there is possibility that there will be something with this ferrosymmetry. So in that case, that gives only 7 SCFTs, right? We have these 3, and this one is Lagrangian conformal field theory. Sorry, this one, the D4 theory. Recently, there's been more work by Argyres and Martonnet and collaborators about classifying, and they have a full list of 16 or 20 something theories. Those do not appear here. They also have are all the cases where they don't have AD type ferrosymmetry in general. They have more complicated ferrosymmetry. I don't have a complete picture of why. But one comment is that all of these I will show are the ones that are naturally, in a sense I will make precise, engineered in type 2B, where the Coulomb range is trivial. So in the sense, my setup is I just have at low energy at the generic point, I have a U1 photon, nothing else. All the other more slightly exotic Argyres-Witten type and Argyres-Martonnet type theories have a so-called enhanced Coulomb range, so they have extra 3 hypermultiplets at low energy on the Coulomb range. So there is extra physics associated to that. I'm not sure. There should be some more general picture in this picture to include that. There are some comments along those lines in Closset, but personally, I don't fully understand what is how they do it. Okay. There's some, anyway, we can discuss later.
Yes,
so,
because they can be realized as S-folds in type 2B. So
yeah, so there is indeed, but here I will not use S-fold, but in principle, there might be. Let's discuss at the end. So that was what appeared in particular also in Closset in this picture. But in this paper, for instance, 3 years ago, they said, oh yeah, they claim correctly, in fact, that in 4D, mean, they say like it's obvious that in 4D, if you can only have this type of singularities, not the so-called multiplicative type, IN, at infinity. So they didn't discuss what happens, while in our picture, we really were clear about those theories from the start. I will show that if you have an IN singularity at infinity, what you define is not strictly speaking, the UV then completion is not 4-dimensional, but 5-dimensional. And we'll get to that. But apart from the fact that the UV is really a 5D theory in a circle, at low energy is very much like an ordinary rank 1 4D n equal 2 theory. And in this case, you will have some nice little symmetry as well, which is of type En, and you can count the number of configurations in the same way. So that's all I said. And in particular, if you have the trivial fiber at infinity, as we said, we'll have not a 6D theory, a 5D theory, but a 6D theory. That will be the so-called E-string theory. It's a 6D n equal 1, 0 SCFT, compactified on a circle. Again, we get 4D n equal 2 at low energy, and that will be all this setup. So in that sense, all of those theories here are just the descendants of the string. I mean, literally there. Okay. So until what time do I have?
You have 20 minutes.
Okay.
Till 40.
So we claimed above that the non-abelian part of the supersymmetry was captured by the singular fibers. One of the reasons I introduced the modular group earlier, the group of section, is that it's also one way to see the full flavor group, even already at the level of the algebra. The point is that while the Skodara fiber gives the actual non-abelian part of the flavor symmetry, the abelian part is given by sections. So for each generator of the free part of the modular group, there is a U1 symmetry at low energy for this particular Coulomb configuration. So an example would be the massless U1, right? Massless or massive, in fact, for SU2, sorry, with an F equal 1. So in that case, well, the symmetry is SO2 and F, so SO2, so U1, so it's abelian. The massless configuration in this case is I plus I1, and you can compute explicitly. If you want, you can do it explicitly. It's been done also in mathematics paper from the 80s, but there is only a single one-dimensional modular group, rank 1, I mean, so it's indeed U1. Okay, so the global form, now I will make a statement about the global form and then try to justify it and also talk to 5D in the next 20 minutes. So the global form of the flavor group can be determined by analyzing precisely the modular group of section. So as we said, it has this form in general, it has a free part and a torsion part. Here, for simplicity, let me assume that the flavor group is semi-simple first, and then I just need to determine the global form of this group. So I have the algebra GF here, and the claim is as follows. So first, I will look at the full modular group of the torsion part of the modular group, and look at all the torsion sections that intersect trivially all the fiber in the interior. So in general, you will have a given section, intersect somewhere or every singular fiber, and then every fiber, but at the singular fiber, you need to determine where the section intersects the various irreducible components of the fiber. So in general, you have, like for instance, the EN case, the I2 case, right? I would have 2 pi1, and you want to know if it intersects the first or the second pi1, the trivial or the non-trivial one, so to speak. So in my Z1 will be all the sections that intersect trivially every fiber except the one at infinity. You always need to intersect at least one fiber non-trivially. So it's theorem. So that naturally defines a subgroup of the torsion part of the modular group. And we are then interested in the co-kernel of the inclusion of this subgroup into the full torsion group. So that's in general then you have a co-kernel there, and that's itself some abelian group. And you can think of the full torsion as an extension of these ideas. Then we claim that two things, that the global form of the flavor symmetry is the simply connected. So you first take the algebra here, right? You take the simply connected group, for instance, spin n or whatever, and then divide by this f here, this group f. And the action of the flavor symmetry group can be determined in principle. Well, in the paper, we don't give too many examples. Hopefully, we will in paper to appear. but the actual action in more complicated example can be determined by just looking at where it intersects exactly at each fiber. In many cases, there is a unique way it could act anyway. And Z1 itself, the subgroup, so those are the torsions that only intersect infinity, the section that only, the torsion section that only intersect infinity, correspond to one-form symmetry of the theory. This is very similar to discussion of the gauge group in F-theory for the F-theory experts, and of course it's not a coincidence. We'll get to that. So this, that was my claim. I will justify it, but to tell you that it can give you non-trivial results. So of course it works for SQCD, so that we knew the result already. At least one result we didn't know was what was the global form of the Argyll-Glass theory. So let's say the H1 Argyll-Glass theory has a SU2 flavor symmetry as an algebra, but the actual torsion is Z2, and then it will be SU2 mod Z2, so an SO3 flavor symmetry. This was actually shown, I mean, we showed that, but then of course we were scooped on this particular result piece by Matthew Wickham. But then thankfully for the next case, their argument doesn't apply to the next case, H2, which is by our argument will be then SU2 mod Z3, because there is a Z3 torsion for the geometry of the H2 Argyll-Glass theory. So again, and that's a non-trivial claim that also checks out with like index computation. Similarly, for the Milan-Meshansky theories, it's also always the centeredness group. So E7 mod it centers Z2 or E6 mod it centers Z3. This claim was also done independently by was computed a bit before our paper by different method type classes type methods by Bardwaj.
And what about the one-form symmetries?
None of those are one-form symmetries. By the you can check that they have all the
So it's just pure SU2 which has a Z2 one-form symmetry, and that's it.
You can actually classify all the one that they've. It's something that I've checked recently. You can look at what are the necessary conditions to have a torsion section in to have a one-form symmetry according to my definition. And the only one that works is indeed this one, which is pure SU2. Is E1 here, which is the 5-dimensional SU2, which also has a one-form symmetry. And is that it? Yeah. So, yeah. Oh, and E0, sorry. E0 has a Z3 one-form symmetry, and that's also a known fact from a year ago. So that's the example for SQCD. You can also compute the section, reproduce the result we said before. So that just, I mean, all of those, I mean, there is a nice paper by Person and Miranda when they actually computed section very explicitly for many of these, almost all of these. So you can just borrow the result from mathematics. And then, as we said, it gives a very global view on the alert configuration. So this is just an example to flash some courageous computation also that Auria did. So what you can do is you start with SU2 and equal 3, as we said, that's 13 alert configuration. That means I can tune my mass parameter in my Seiberg-Witten geometry to get all these kind of singularities in the interior. So the generic case is, so I1 star is always at infinity, but then the generic case, when the masses are generic, I have 5 I1s, but then they can try to collide in a given way, right? And that's all the alert configuration mathematically, but that's also all realized physically by the known Seiberg-Witten curves. And you can check that. So in particular, to answer also the question earlier, in this case, there is a type 4 singularity that you can reach to, and that corresponds to the Argyll-Glass point. When you zoom in onto the type 4 singularity for this configuration, that means you tune one mass to be lambda, and you get this Argyll-Glass theory.
So as you tune those masses, there are some states in the DBS spectrum that become massless.
That become massless and visually non-local. We'll have a picture of that, I think, in a minute, using modularity, actually. So another ingredient that I will briefly flash is the role of modularity in this story. So many loci, by no means all, I mean, it's not generic, but many, like, in some sense, many interesting ones. On this extended Coulomb branch, thank you.
Thanks, Thomas.
Many special loci have so-called modular properties, meaning that in many interesting cases, the Coulomb branch is a modular curve. They call that the modular curve is just a quotient of the upper half plane by a modular group, so subgroup of SL2Z. When this happens, so when the Coulomb branch is modular, is a modular curve, that means that there is an isomorphism between the gauge coupling tau and the parameter u. Then this function u of tau that relates u and tau in general, in that case, it will be an isomorphism, like I said, with a particular fundamental domain of the 4 gamma on the upper half plane. I'll put a picture right now. So in that case, then u of tau would be what is called a Hopf module or principal modular function for the particular modular group gamma. And when this happens, when the Coulomb branch is modular, the singularities are in one-to-one correspondence with cusp and elliptic points of this modular group. So then you get a much cuter way of analyzing singularities using like standard theory of modular groups. So a well-known fact is that pure SU2 is modular. This is the famous gamma 04 curve in the second Seiberg-Witten paper. Slightly less known is that n equal 2 and n equal 3 are also modular. And that was, I think, first shown in a little paper, a nice little paper by Nam in '96. So they're actually all conjugate to each other, the group. I mean, you see that n equal 3 is gamma 04 downstairs, gamma 04 upstairs. But the fact that they conjugate to each other, I mean, it gives different physics because it's different. It corresponds to essentially putting different cusps at infinity. So for pure SU2, that's the gamma 04 modular curve, that's the fundamental domain. And so you write the U plane mapping into the top plane as a fundamental domain for gamma 04, and that gives maybe a very neat picture of the physics. So there is a I4 star cusp at infinity. So it's a so-called width4 type cusp. And then that so-called width1 cusp at, in that case, tau equal 0 and 2. And of course, you can have many choices of another domain. That's one choice. That's another choice. They're equivalent for different things.
It's mathematical convenience, but what's the physics consequence of not having modularity, for example? For n equals to 1, you say that it's not a modular curve.
Yeah, it's. I don't know if I have a full answer to that. So there is some nice paper that I can refer to, which today. Yeah, here. In the last year or so, there are two nice papers by Manschat and his students. When they look at, in general, this map, even when it's not modular. So what happens when it's not modular is that instead of having an actual fundamental domain, you don't have, it's not single valued, it would be essentially branch cuts are on various parts of what you would still want to call the fundamental domain. I'm not sure what is the full physics. It seems that related to things that we care about, the BBS quiver can become much wider. In a sense, the mutation class can become much wider when it's not modular. So in a sense, modular make it thinner, but I don't have a full picture. Yes. All right. So, but technically, when you have this picture, it allows you to read the singularities much more efficiently. So for instance, because we know that it will always be, I mean, the cusp and the elliptic point will correspond respectively to either IN singularities or maybe I star, or instead type 2, 3, 4 for the elliptic points. And you can read off from the fundamental domain what it is, and you can read the actual monopole metrics by just, for instance, in this case, the monopole point is there, it's conjugate to T, but the conjugation matrix is just S, and S just because the T would be the cusp at infinity, you conjugate it with SL2Z, in SL2Z to get it there, you conjugate by S. Here you do T2 and S, that's my conjugation matrix T2S, and so on. So this gives the kind of very visual picture of seeing which are the monopoles that become massless, which giants become massless where in this fundamental domain.
Just 10 minutes for the 5D story.
Okay, 10 minutes. So yeah, that's just another example, but that's an example for SU2 and equal 1. That's the fundamental domain. Here there is an elliptic point, the type 2, and that's the Argyll-Plus theory. So you can also see those Argyll-Plus point there. All right, so indeed, 5D SCFTs. So as I said in the beginning, I'm interested in non-compact Calabi-Yau geometries that will engineer 5D theories in M theory. We expect in general some sort of map from threefold singularities, Calabi-Yau threefold singularities to 5D SCFTs. This map is poorly understood in general, but in many cases, well, we know many examples, but the most basic quantity is the so-called rank of the 5D SCFT, which is just defined this way geometrically from M theory. The rank is the number of exceptional divisor of any Crepent resolution, a generic Crepent resolution of the singularity. So if, for instance, you have the conifold, you resolve it, there are no exceptional divisor, it just resolve conifold. In that case, it's just a free hypermultiplet in 5 dimensions. Then you can start doing more complicated singularities. There will be various exceptional divisors, and the number of them is the rank. Because to each of them in M theory, you will associate a U1 low energy photon. So that's why it's again a 5D Coulomb branch. Okay. So a lot of things is known about that. It's been known from the 90s. That's the general picture. In general, you can resolve a singularity, you get a Coulomb branch, Monsieur de Coulomb, and you can deform a singularity and you get the Higgs branch. So here I focus in rank 1 theories. So those are all, the resolution is always the total space of a del pezzo surface, of a Fano surface. So it's either del pezzo, so E2 blown up at up to 8 points, or F0, which is pi1 times pi1. You can see the dPn as equivalently as blowing up pi1 times pi1 n minus 1 times at generic points. And that will be the geometry of that, the physics of that, sorry, will be essentially 5-dimensional SU2 with nf equal n minus 1 flavors. Just from M theory, you can also read off the flavor symmetry of these 5D theories from the intersection pairing of these resolved singularities, which all have, for dPn, they have En type intersection pairing. Like the intersection pairing is as an En, and then there is a one-dimensional direction along the canonical divisor. So these 5D theories then have En symmetry. That's the usual series of En. So by En, I mean E6, E7, E8, E5 is D5 and so on. So this theory was discovered by Seiberg in '96. As I said, they correspond to essentially the UV fixed point of 5D n equal SU2 theory with NF minus 1 fundamental. Or more precisely, what you start is with an abstract SCFTs in 5D with the En symmetry. There is a particular mass, an abstract mass term you can turn on. Upon RG flow, it flows to SU2 with NF equal n minus 1 fundamental. Recall that in 5D, gauge theories are IR3, so it's a free theory which has with a cutoff, and the UV completion is a 5D SCFT. So now we want to consider those 5D theory compactified to 4D to get back to our setup. So we just put them on a circle. So we now have that's what I said. What happens is that in 5D, you have the 5D n equal 1 supersymmetry, which has a real scalar. You put them on a circle, as usual, the scalar gets complexified by the holonomy of the gauge field around the circle. And then we get again a complex scalar in 4D, pretty much like, I mean, it's an ordinary 4D n equal 2 theory, except that in some sense I have an infinite term of eigenmodes. So it's just a theory with infinite number of fields in a rough sense. Okay, let me skip that, but in principle, we can look at we have then the ordinary Coulomb branch and some BPS spectrum, which are M2 branes and then D2 branes type 2A. Okay, so the actual parameters that replace my U plane is will be what? Well, the only subtlety here is that my A field now, my low energy photon, comes from this compactified gauge field in the field direction. So there is an extra gauge symmetry that shifts A to A plus 1 because of the large space transformation around the circle. So A itself, or A squared itself, semi-classically, like in 4D, is not a gauge invariant parameter. What is gauge invariant is e to the 2 pi I A plus A to the minus 2 pi I A because of the Weig symmetry. So this kind of thing is gauge invariant. While semi-classically, this thing is just the expectation value, again, classically, of a Wilson loop of SU2 in the fundamental. It's a supersymmetric Wilson loop for the SU2 theory in 5D. And so by definition, U will be then the verb of this Wilson loop on the circle. And that's what I want to consider as the base of my Seiberg-Witten geometry. And apart from that, everything is as before. You want to understand what is the low energy dynamics, understand the Seiberg-Witten geometry. So the Seiberg-Witten geometry can be derived by essentially a string theory consideration and from these strings. So it was derived by Canor, Morrison, and Seiberg in '96. And I think with all the mass turned down, the full completely coherent one was done by Eguchi Sakai in 2002. And that's our starting point. So I will not flash any curves, they're complicated, but they're there and well known and depend on all the EN parameters, mass parameters. So the Seiberg-Witten geometry is essentially local mirror symmetry. So here we have 5D in theory. We compactify on a circle that gives us type 2A. And then we do a mirror symmetry to a mirror threefold in type 2B. Then you get a one-dimensional vibration over the U-plane that essentially the mirror threefold of the singularity I started with. I start with the resolved singularity, I do a mirror. So in the toric case, it's very well known, like in those papers and in the Orivafa mirror symmetry. So yeah, in string theory, then in type 2A, I have scalar parameters, which are my low energy photon A and the masses. In the mirror, I get my U, the wave of the Wilson lines, and various masses, which are just exponentiated little mu. And then I have a mirror map between the two. So for the masses, the mirror map is always trivial, essentially because it's their parameters, not moduli. But for U, there is non-trivial map between A and U. So semi-classically, it will be just like this. So that's just the inverse at large U of this, right? Sorry. But then there will be instantaneous correction in the usual sense. So that's the mirror map that you want to determine in principle. You can through many methods. So yeah, so that's the. Let me skip that. So you can do essentially that is pretty familiar to many of you. I think you can compute the period either in type 2A or in the mirror. In type 2A it will be Seiberg-Witten, I mean the usual form of Witten theory. Do I need that? Okay, so the way we're going to write the mirror is as follows. The mirror can always be written, instead of, it's actually in all these families, for the EN family, it will always be an hypersurface. But it's useful following a trick by Rencontres of writing it as a double fibration over a plane. So instead of having one equation in C4, you get two equations in C5, essentially. So you write it like this: f of x, y, and u would be my Seiberg-Witten geometry. And this Seiberg-Witten geometry is itself embedded into a threefold. So there is just an extra direction. In other words, the picture is that you have a threefold, which is the W plane, there is the fiber, the T2 fiber over it, and there is an extra C star fiber. And that in the total space is a threefold.
Time is basically up.
Okay. So while doing that, you can compute the flavor symmetry by a relatively standard method now in type 2B. And yeah, and borrow. Yeah, so that way you can prove that, then you can see in the slides or in the paper. The claim I said earlier by just using the actual symmetry. Let me just check one little point I said earlier. The claim was that the 5D theory of a circle had an IN singularity at infinity, similarly to the 4D case that can be determined using semi-classical arguments. So there is a one loop potential. You just need to resum some KK modes, but otherwise it's like a one loop potential. So instead of having some log in 4D, we have some trilog in 5D on the circle. But from that, you can already compute the mode at infinity and confirm that it's T. And yeah, so from that you can play many games, but I gave the gist of it. Let me conclude maybe here. That's an example of, again, using modularity, a very cute picture of the full massless Coulomb range for the E1 theory, which is like 5D QSU2 at infinite coupling. So there will be a particular diamond that becomes, well, there is a monopole that's massless, two diamonds that condense together, and one monopole here. And you can play out of game like that. And finally, because you can easily compute the electromagnetic charge in this picture, you can look at their pairing between each other and assume that there is a way in which, well, you can go near the point here, for instance, and have an effective description of the BBS states of the spectrum as one state of this, the very light particles from the Seiberg-Witten singularities. So you can look at the intersection pairing from that, get a BBS quiver, And that would be one of the non-devious quivers for this theory for the local, in that case, local F0. And similarly here for E8. So thank you. Any questions?
Yeah, so do you consider twisting when you compactify 5D to 4D?
No. I mean, no, we don't.
Yeah, because that's where the S balls would come from. So then I guess this answered the first question about the rank 1.
Yeah.
They all come from twisted compactification from 5D.
From 5D or from 6D?
From 5D.
Okay, you can, yes. Yeah, indeed. So the question is to understand that in the mirror. I mean, in type 2 picture in a clearer way. But mathematically, it should be an extra ingredient, like that keep track of this twist or the S-fold in F theory language in this kind of rationalistic surface, which I'm not quite sure what is the correct mathematical statement.
So I'm a bit confused about this general description in terms of rational elliptic surfaces. So as Amir was also mentioning, from the point of view of the fibration, there's a symmetry between all fibers. You can decide one is the fiber at infinity or not. But at what point does this choice enter in determining the special Keller metric on the Coulomb branch? Or is there?
Yeah, I mean it does in a sense. Well. I'm not sure. Let's see. At least if you want to connect to superconformal field theories, when there is a even simpler conical special Keller structure, then it does determine it in the sense that in the like Arguelles et al. Papers, they would consider so if I have a type 2, let's say at infinity, you get that means 2 star at the origin, and so you get this conical metric with the 2 star singularities, and so that determines. In that sense, it determines when there is conformal field theory, it determines which it is. But the statement is that it determines the UV. I mean,
the Seiberg-Witten differential isn't encoded in the elliptic either, right? That's additional information, and that's where the use depends.
It's just the integral of the canonical one form of the fiber. So the canonical one form does not know about the choice of fiber at infinity. Maybe once you integrate it back to the
when there's a choice to be made, you're not saying that as soon as you specify the curve, you have the differential.
That's a great point, and it's something that for most of what we do, we can skip, assuming that in some sense we can be generic. Let me explain. So indeed, I said here that from this point of view, you know, for all this geometrically, we only care about the rationalistic surface, and then we know, I mean, there is a unique holomorphic form and so on. There is extra data indeed when you integrate back to get the Seiberg-Witten differential, what are the poles? So that gives you what kind of flavor structure in particular you can have. The poles are related to the masses of the flavor symmetry. And so if you look at like the classification story of Arguelles et al., they would have, they have specific what they call deformation pattern when you would have specific mass that can appear in the pole. That give, for instance, instead of giving the full E8 theory or Milanowski theory, they could have only, I don't know, F4 or some of the funny subgroup there. And what is not very clear to me though is what orders, I mean, there's various constitutive conditions about what deformation patterns are allowed, what kind of masses you could have. But mathematically, is there a statement, I mean, one, because their Seiberg-Witten theory, Seiberg-Witten curve for the more complicated SCFTs, at least to me, they look, I mean, they are exactly, if you look at the Seiberg-Witten, even the differential, they look like specialization of the generic, the more general one that I'm discussing here, but with specific masses. And then funny things can happen at specific masses. And I guess my question is, that I don't have a good answer to yet, is there a more natural mathematical way of imposing those physical requirements that they have? But yeah, I mostly skipped under what are the conditions of Seiberg-Witten differential. There is a bit more discussion along those lines, I think, in Gauss and Chicote. But I think that's indeed part of the crux of the matter, is to specify what are the allowed system of solution to Seiberg-Witten differential to get a family of lambda Seiberg-Witten that will be consistent with a given flavor symmetry, a given SCFT.
Is it conceivable to extend these methods to rank 2, for example, in terms of classifying all rank 2?
I mean, of course, this thing is very, very dependent on having elliptic fibration and all the nice things that come with it. In principle, that's the usual difficulty, right?
There will be some higher dimensional torus fiber or some higher dimensional.
You have a genus 2. I mean, if you go naively, it's a genus 2 fibrations, and as far as I know, they're not classified. There's been some good, interesting work there about what can happen at codimension 1. Those recent work by Martonet and Arguelles and Martonet. There's some general constraint, and there also be some recent paper with Ceccotti and Del Zotto, when there's some more like general constraint, but actually not in the generic case. But there's some interesting. When there is like when a U1, there's some very interesting constraint at any rank when the U1 R symmetry is broken to a discrete subgroup, which is non-trivial on the Coulomb range, then you can see a bit more. But yeah, in general, I think it's still wide open how to classify theories at a rank.
But from a geometric understanding point of view, that's rather trivial to classify toric surfaces with the high.
Is it? I mean, I don't know. I don't think there has been.
Toric calabria has been.
Well, most of these are not toric, right? Toric, for the toric case, yes. I mean, we have the orthogonal symmetry and we know everything, but that's a very, very small subset. Even in this case, right? So I went a bit fast maybe, but there is a series of 10 EN theories in 5D, and only E0 to E3 are toric. They're toric calabrias. The other one are not, and yeah. So in general, it would look like you need a Kodara type theory of higher genus vibration. I don't think there is that much known on that.
Well, probably, I mean, I think like we're just saying, instead of looking at higher genus Riemann surfaces, a little bit higher dimensional tori.
The Jacobian.
Also, looking at the Jacobian directly, yes, absolutely. Yeah, okay.
So there is a classification by Og and some other people about in dimension 2, I think. But it's very hard because I think they already have like 50 cases.
Okay.
Cool. Any question from online people? If not, let's thank Cyril again for the great talk.